Okay, so let's take a look at the next example. I've got this object being towed by two ropes. They're not acting in tandem, they're acting at angles to one another. In fact, they're acting at bearings to one another, so I'm going to start thinking about a compass. They tell me the resultant force is 1,000 newtons, due north, straight north, but they didn't tell us what's going on with each rope. So we need to figure that out. So I've got my compass. I've got one force going north 30 east. I've got one force going north 20 east. Sorry, north 20 west. They're acting against one another. So between them, really, they're acting at an angle of 50 degrees to one another, right? I know that a resultant is formed when I complete the parallelogram. So let's do that. The parallelogram goes like this, and like this. And I know my resultant force has to go due north, and it goes from my tails to the heads. And I was told this is 1,000 newtons. As I was saying before, we recognize that our initial question had the tails acting at 50 one another, which means, using our C pattern, this has to be 130. And the question is asking us for the magnitude of the tension in each rope. So two different forces. We can call this, I don't know, force 1 and force 2, or tension 1, tension 2. Those are just forces. And it asks us for the magnitude, just the size of those two things. So how can we go about approaching this? Well, here's some nice tricks. 130 is across from 1,000, and force 2 is across from 30. Well, that's a sine law question. So I can write down that the sine of 30 goes with force number 2. And I know that the sine of 130 is across from 1,000. And I can cross multiply and solve this. So we do what we got. F2 times the sine of 130 equals 1,000 times the sine of 30. Divide them both out by sine 130. They'll cancel. Divide this side by sine 130. And force number 2 has to be 652.7 newtons. Okay. So like we did previously, if I know the resultant of something, I can also figure out the forces that compose it, the components of force. We did it with the lawnmower and the horizontal vertical force. Here my forces are just acting at different angles. You can do the same thing to figure force number 1, just a different combination, right? So we have the sine of, well, we've got 30 and 130. This piece up here has to be 20 degrees to make the triangle add up to 180. So sine 20 goes with force 1, and sine 130 over 30. We already knew that one. Okay, do the exact same process, cross multiply and solve the exact same way. And force 1, if you do it right, should come up to 446.5 newtons. Okay, and that's basically what we do with applications of forces. Okay. If we look at the next idea, so we've got 3 vectors now. Okay. Something we should know about 3 vectors. Always, always, always true. If they lie in the same plane, they have to form a linear combination. We've talked about that in the past. And when they're arranged head to tail, they have to make a triangle. They have to. If they're going to be in equilibrium, the 2 vectors have to balance each other out. So no matter where I start, I can move these vectors around here. I had an A and a B and a C. If I put them tip to tail, they have to make a triangle. Doesn't matter which 2 are working together. Maybe it's these 2. They have to be able to form the triangle if they are in equilibrium. If they aren't in equilibrium, well, then they won't form a triangle. So if I'm thinking about my geometric vectors here, or the size of the vectors, okay, the sum, we're looking down this idea down here, of 2 sides must always be greater than or equal to the 3rd side. They have to be greater than. Right? Common sense says, well, if I have one vector that's 2 newtons, another vector that's 5 newtons, and this vector is 10 newtons, well, there's no way those things are going to be in equilibrium because 2 plus 5 can never even equal 10, even if they're acting in the exact opposite directions. Okay? So 2 of my sides must be greater than or equal to the 3rd side, always, 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 always. Okay, so for example, 4, 12, and 20. Why can't they be in equilibrium? Why is that not possible? No matter how I draw them. Well, if I had a 4 newtons and I had a 12 newtons and they walked totally in tandem, that's going to make 16, right? Well, the third one, to balance it out, is more than 16. I can't balance a 16 with a 20. That's not possible. Okay. So remember the idea, that two of them have to be equal to the third one, at least the third one every time. Okay, so if we look at the second example here, I got 7, 12, and 15. Well, if I combine 7 and 12, that's bigger than 15. If I combine 12 and 15, that's bigger than 7. And if I do 7, 15, that's bigger than 12. There's no combination. If I take 2, it won't make at least the third one. Okay, so this one can be written in equilibrium. Somehow, some way, the 7 and the 12 can equal the 15. They can balance each other out. So the question asks us to find the angle formed between them. And on the previous screen it said the angle we use is always the angle between the two smallest sides. So we're looking for that angle there. That's our equilibrium angle. To do that, knowing three sides, I can use the cosine law. The cosine law states if I take two sides, sides B and C, and those don't matter, the order of them, so 12 squared plus 7 squared, and I subtract the third side, the A side. Remember, these two things are across from each other in the picture, right? And divide by 2 times B times C, I can get my angle. So we put that on our calculator, and then we'll take the inverse of that, because we're looking for an angle. You should get an angle of 101 degrees. So these three forces can be in equilibrium as long as the angle between 7 and 12 is 101. Okay, so let's look at velocity. Velocity is the second application. It works basically the same as forces. We can work with right angle diagrams. We can work with non-right angle diagrams. It depends on how the question is set up. And we've done one like this before, actually. We got a plane traveling due north, airspeed of 900 kilometers an hour. It encounters a wind from the west, which means it's blowing towards the east. And obviously that's way bigger than scale, but 80 kilometers an hour from the west. I want to know the resultant velocity of the plane. So my plane was blowing off track. It ended up here. Okay, so it's going northeast at a certain speed. And by saying the word velocity, I'm talking about the vector idea that has a size and a direction. So like we started with today, we can use Pythagoras. Pythagoras will just be the square root of 900 squared and 80 squared. It's a nice quick one. Put in our calculators, we get 903.5. So the wind has helped the plane just a little bit. It's gone a little bit faster than it was. But it also blew it off track. And we can find the angle we're going at now by using tan again, just like we did the first one with Chloe and Buffy and pushing that crate. Okay, and my opposite is 80, my adjacent is 900. Take our inverse, it's a really small angle. Angle is only 5 degrees. Okay, so where's our plane going now? Well, the plane is flying at 903.5 kilometers an hour. Because the velocity, we need to have a direction. Our direction would be north, 5, east. Okay. That would be our angle right in here, right? Okay, so we can do the nice simple ones, the right angle one. We can also do ones that are not right angles, like we did with the forces that are acting against one another. So last example here, we got a plane head north 30 east. We're talking about bearings, we need compasses. So north 30 east. It's going 800 kilometers an hour. It encounters a wind of 75 blowing in the direction of southeast. Okay, so another compass. My wind is going this way, and it's southeast, which means this is 45. It also means that's 45. My plane, which was trying to go northeast, got blown off track a little bit, right? It ends up over there. So our objective in this case is how fast is the plane going? What angle is it going at? Now the trick with this one, because you have two compasses, you remember back to grade 10, is you should always have a Z pattern. So if you think of this as a Z, if this is 30, so is this, which means this combines to make 75 degrees. Okay. We knew the wind was 75 kilometers an hour, and we knew the plane was going at 800 kilometers an hour. I've got two side lengths and an angle between them. That's the cosine law. So x squared equals 800 squared plus 75 squared minus 2, 875 cos of the angle between them, which is 75. All in our calculator, square root it, and we get 783.9 kilometers an hour. So the plane's actually been slowed down by the wind this time. If I want to find the angle I'm going at, to find angles, use the sine law. So we match up the things we know. We know sine of 75 has to go with the 783.9 we just found out. And I want to find angle y. So that's going to go with the 75 kilometers an hour. And the reason I want to find y is, we go back to the initial part of the question where the plane was leaving from the airport, the starting point right there, if you will. Okay, so we want to know our difference from there. Cross multiply and solve that. And hopefully you guys will get y equals 5.3 degrees. So for our therefore, our answer, we say the plane is flying at 783.9 kilometers an hour, and it's flying, well, it was originally going north 30 east, but we've added a little bit to that, right? The addition of y here. So it's not 30 anymore, now it's 35.3 degrees east. Okay, and that takes us to the end of velocity and forces and how we can apply them in the real world. We're not going to do a ton of stuff. We sort of save that for the physics course if you want to take physics, just to get the idea of how we can use this two-dimensionally at least. Oops.